Welcome to Intelligent Systems, an introduction to artificial intelligence. My name is Schroeder and I'm a professor in bioinformatics at TU Dresden. In this introduction to neural networks, I will introduce the basic concepts behind them, such as a neuron. I will illuminate why neural networks are so successful today. We will look into various applications of neural networks, and then we will look into the history of artificial intelligence and what there is out there beyond neural networks. So let's start off with the basic concepts behind neural network, and that is a neuron. And we will start with a neuron in a brain rather than in a computer. So for this, we have to go back to the year 1899 when Santiago Ramon Cajal visualized neurons, as you can see in the picture. He received the Nobel Prize for this. And if we abstract a little bit from this, then a neuron, as we can find it in the brain, consists of dendrites that receive incoming signals. And then there is a cell body that processes these incoming signals, and it fires an outgoing signal when some threshold is reached. This outgoing signal is transmitted via an axon, and the axon is connected via synapses to another dendrite. And this can be abstracted in a computer. The dendrites correspond to some input xi. The cell body is a computation where we take a weighted sum of these inputs and put them through an activation function h. This produces some output which corresponds to the axons, and this output is again the input of some other neuron which corresponds to the synapses. And then we create a more complex organization of such individual neurons. So we connect outputs to inputs and we organize our neurons in layers. And here you see on the left the input layer, on the right the output layer, and in between the hidden layers that do the processing. Conceptually, one can view a neural network as nothing but a mathematical function fw of x equals y, where x is the input, y is the computed output, and the function that does the computation is fw. And the w are the weights, the parameters, which are used to weigh the input. Let's give a more practical example of what that means, that a neural network is nothing but a mathematical function. One task when neural networks are successful is image classification. And one specific image classification task is the identification of digits in images. And there's a very well-known data set called MNIST, which comprises 70,000 handwritten digits. And you can see examples down here for the different variations. And essentially what we're looking for in a neural network is that it's a function fw that takes such an image as an input and produces as output, in this case, the digit 5, or here takes another image, which is already a bit more difficult to identify, and produces as output the digit 8. Now, how does this practically work? The image is nothing but a set of numbers, or rather a vector of numbers. So we have 28 by 28 pixels, and each pixel is encoded by a number. If we have a binary picture, then maybe it's a 0 corresponding to white and a 1 corresponding to black. And that means we have here the corresponding amount of input neurons, and each input neuron represents one pixel in the image. And for this classification task, we have just one output neuron, which would comprise the digit 5 that we would like to identify. However, the function fw is very peculiar because the input x and the output y are very low dimensional vectors, and w is very high dimensional. Take as an example the MNIST digit classification. 28 by 28 pixels is 784, so x is a vector of 784 dimensions. Y is even smaller, it's just one dimensional. is really just the digits from 0 to 9. However, W is typically in the range of millions. For example, 5.7 million for a neural network called SimpleNet, published in this article over here, which achieves for MNIST and also for other classification tasks already very good results. So, and that is really bizarre. Small input, small output, but in between heavy processing and many parameters. So why is that? Why is W so high dimensional? And if we consider the input layer with 784 dimensions, and we connect it to another layer, and it's fully connected, that means every neuron in one layer is connected to every other neuron in the other layer, then this adds up to 784 by 784, and that's already 614,656. And you can see that depicted over here, one layer and connectivity between all of them. So you have a quadratic explosion between the layers. And if you would now connect 10 of these layers, you have already 6 million weights. So that's the explanation why there are so many weights. Now, an important concept in neural networks is forward propagation, and that means that the signal which we receive at the input is propagated layer by layer towards the output. And in each step, layer by layer, we compute the weighted sum of the inputs for that layer. We pass it through an activation function. And we represent this here with the inputs x, the weights y. Here they're summed up. The activation function is h, and it produces the output y. There are quite a number of activation functions that are useful. There's, for example, the logistic function, which maps negative values to close to 0 and positive values close to 1. And it's basically a smooth transition. Tangens hyperbolicus, which is also a smooth transition, but not between 0 and 1, but between -1 and 1. And then there is the rectified linear unit, which maps negative values to 0 and positive values to themselves, to identity. So, and these are examples of this activation function h over here. So how can we judge the difference between the values that the neural network predicts and the known values? So for the MNIST example, we knew that it's a 5, and so if the network produces 5, that's good. So how can we quantify this? And there are numerous loss functions that measure the difference between the predicted output and the real output. And one is the mean squared error, MSE, which is 1 divided by n, so we have n examples, and we sum up the difference between the known value and the predicted value, and we build the square. The reason we build the square is that we want to exaggerate large errors and differentiate that from small errors which are not so important. In contrast, we have the mean absolute error, where we don't build the square, but we just take the absolute difference. And a third example is the cross entropy, where we use the entropy formula to measure the similarity of y and y star. Note that in general, the error function is usually abbreviated with a capital E, and generally we will denote the known values by y star, or sometimes in the literature you find y hat, and the computed value as y. However, you should always be alert. Of course, this is not completely consistent throughout all of the lectures. Now, we have swept forward through the network. There's also direction backward. And this back propagation we use to adjust the weights. So given a certain loss that we have computed, so given a certain error that we find, how can we change the weights to reduce that error? And the two key questions in this context are into which direction to change the weights and by how much. And for this, there is a very fundamental technique, which we'll cover entirely in the next lecture, called gradient descent. So what we will do is we will build the derivative of the loss function E with respect to the weights W, and we will change the weights into the direction which minimizes the loss. And this use of gradient descent and the concept of backpropagation was absolutely fundamental to make neural networks feasible for larger examples. And they're one of the key reasons why they're successful today. And formally, we represent this derivative that we're building as delta E by delta W. So these deltas you know from your math classes, it's the Newton way of writing down the derivative, in contrast to what you probably used in your math lectures, the F prime notation, which it was coming from Leibniz. But in neural networks, it's usually the delta notation that we're using. So what we're interested in is delta E by delta W. Now, the second question was by how much to adjust the weights, and that's the step size alpha. And we will see that if we have alpha too small, then we make no progress in improving our neural network. And if we make alpha too large, then we cannot find an optimum that reduces the error. So formally, we denote what we're after as W becomes the existing W plus alpha, the step size, times delta E by delta W, the derivative of the error. So a key challenge in neural networks will be the computation of delta E by delta W. And we will introduce the concepts behind this in this lecture, and we will have an own dedicated lecture to the computation of delta E by delta W coming up later. Another concept are epochs and batches. The question is, how long does the process of forward and backward propagation actually last? And that is important. Neural networks are there to be trained, so they're meant to be learning. That means we must have training data. In order to assess how good the neural network is, we also have test data. These should always be strictly separated, because if training data and test data get mixed, we just learn by heart. So let's assume we have this training data and we adjust the weights of the neural network, and then we denote an entire pass through all of the training data as an epoch. And typically we can run trainings for several epochs. And the question is, after seeing how many examples, we adjust the weights. Do we see one example and we immediately adjust all the weights, which is quite a bit of work? Or do we look at a couple of examples and only then adjust the weight? And this variable is the batch size. And it can be one example, or it can actually be all of the examples, in which case a batch would equate an epoch. However, typically for practical neural networks and larger ones, the batch size is 32, 34, 128, 256. And as an example from MNIST, you heard already it was 70,000 images, 60,000 are for training, 10,000 for testing. That means that epoch in MNIST is 60,000. So the main research that is today going on in neural networks can be categorized somehow along the simple formula Fw of x equals y. So, and I think the most prominent question is how to determine the W and how to determine the W efficiently. And this has an algorithmic component to devise algorithms that can do this as best as possible and as fast as possible, but it also has a hardware side to it. So that's where GPUs come into play, because turns out that on GPUs you can do the calculations that the algorithms need for the adjustments of W. On a GPU you can do them much, much faster. And that is one of the reasons why NVIDIA, the producer of graphic cards, is today such a large company that whose stock market value is just rising and rising. A question is, how large does W have to be? How many parameters do you need? And this is tightly intertwined with the question of which structure the connectivity between the neurons should have. What is the size? What is the layering? What is the overall architecture? And then there is the training data. So the x and w prime. How much of this training data do we need? How does the amount of training data correlate to the error? What quality of the data do we need? What happens if the quality is poor? How much does the neural network improve as the quality increases? How can we ensure that the data that we have given is representative of the problem that we have, and that we have made a good split between the training and the test data? And a final question is, how do we actually represent that? You've seen already that for MNIST, we represented a picture as just a vector of numbers. That might be RGB values or black and white. If we think of numbers, then at what precision? Floating point numbers, 16 bits, 32 bits, 64 bits. Of course, 64 is better, but given the quadratic explosion that we saw over the number of weights, the larger this precision gets, the more memory we will need. Maybe also a binary representation is much more compact and faster. So all of these issues are current research questions that people are working on. Okay, so with this basic concepts in neural network of a neuron, the layering and the forward propagation, the backward propagation, and the error, now let's look into why neural networks are so popular today. And we will look into 4 aspects. The main aspect is image search and image classification. Then we will look at standardized libraries for neural networks, the growth in compute that happened over the last decades, and the growth in data. But let's start with the most important one, the image search, which is really, or which was, the driving force for neural networks. And here a tiny little history, because you can pin it down pretty clearly of what really the force was that was driving the success of neural networks that we see today. The research on neural networks is pretty old, and of course predating the year 1998 when Google was founded, you have already a lot of research going on neural networks. However, at that time point, the compute was not there yet, and the neural networks in use were not yet really solving large practical problems. So anyway, 1998, Google went online, and at that time it supported only text search. Then in the year 2000, it turns out that the most frequent query that Google was getting was for an image. And that led Google to introduce image search in the year 2001. However, at that time, image search was really, really poor. And the reason why it was so poor was because it relied on metadata, such as the file names or the text that was on the web page surrounding the image. But you can imagine that file names are usually not very informative. If you think of your camera pictures that are called JPEG 5073, that is not very useful in order to be able to search that file name. So in those days, image search was really poor, but Google too couldn't do it, but nobody else could do it too. So there were no alternatives. So in 2006, 5 years later, Google launches Google Image Label. And that was really a funny thing, because it was a game that they put online in which you were presented with an image and you had to type in a label. So for example, sunset by the beach and a dog. And then if somebody else gave exactly the same label, then you got a point. I always wonder who the hell is playing such a game, but Google was big enough that there were enough people doing that. Now, of course, one reason why Google would be doing that is not to make the people so happy and become a game company, but it was to generate data to address the problem that they had with their poor image search. And amazingly, you can still try Google Image Labeler today, still 20 years on, and I highly recommend going there. So you can follow the link in 3 here at the bottom, because it shows you really, really also to a human, very difficult examples where you really have to think a little bit, do you agree, is that label correct or not? It shows you examples with labels, and you have to decide whether that is good or bad. So, and the examples are tricky. So they're still on it. In parallel, in 2006, there was Fei-Fei Li, professor, I think, then at on the East Coast in Harvard or Princeton, and later in Stanford, who initiated the ImageNet repository for ImageNet classification. And this went online in 2009, and ImageNet was really a very, very important resource for neural networks. The idea of ImageNet was to take WordNet, which was an English vocabulary. It contains lots and lots of terms together with their synonyms, but also sub-concepts. And the ImageNet people took WordNet and took 22,000 of its categories and then went online and retrieved images. And overall, they built up 15 million images in these 22,000 categories. They were manually validated. And the idea was that they serve as a resource in order to develop algorithms that automate the categorization. And with 22,000 categories, you can imagine how complex it is. If I remember correctly, then an average English-speaking person has about 3,000 words or so. And Shakespeare is so difficult because he could use 60,000 words. So that gives you a picture that 22,000 is really quite a lot. And for you to get an impression, visit the URL, which you can find at the bottom, for images of dogs. And they have 120 breeds of dogs. And I bet even if you're a dog lover, you probably just are able to name a handful of dog breeds. So that illustrates the vastness of 22,000. And that also led the authors to make the competition on ImageNet a little bit simpler, in that the goal was to successfully predict 1,000 of the more high-level categories of the images. Okay, so ImageNet went online with a competition, and the task was to get pictures which had a standardized size and RGB values, and then to categorize them properly. So when you look at these images here, then you see here clearly, okay, that's a container ship, that's pretty easy. This one here is already a bit more tricky because, well, it looks like a leopard, but of course there are also variations of other cats that look like leopards. Here, this is a bit difficult. If you watch closely, you can see that that is part of a scooter. And this is tricky. At the high level, you see immediately that this is an insect, but only half of it is shown. And which specific insect is a bit difficult. In fact, turns out it's a mite. So that was the task, and you see already that also to a human, this is not trivial. And then came AlexNet. So in 2012, there was one system that really made a big splash. So as I told you, also for humans, it's not trivial to solve these tasks, and that meant the baseline was the human error rate, and that was at 5.1%. Then in 2011, just a couple of years after ImageNet has launched, the automated system were at an error rate of 26%. And then in 2012, AlexNet came around, and that was the first time that a deep neural network was used, and it reduced the error margin by a whopping 10%. And then you can see here in the graph how the improvement went on. Then after AlexNet, it was very fast success. 2013, another 5% better, still 8 layers to the neural network as AlexNet had. Then a year later, 19 layers, then 22 layers, then 150 layers, and so on. And by the time it was at 150 layers, the error rate was below human, and here it ended at 2.3%, so way below the human error rate. Yeah, and when you look, this layering, this increase in layering goes, of course, hand in hand with a massive increase in the amount of parameters in the weight matrix W. And this goes hand in hand with better use and more use of compute. But the key was AlexNet here, because that was the first time that a deep neural network was used for this task. And here you can see the paper. It had 3 authors, and in fact, all of the 3 authors, Kruszewski, Sutskever, Hinton, joined Google, and Sutskever actually later founded OpenAI, so it's a pretty small circle. And what is pretty amazing and a really great achievement that I think is absolutely deserved and cool, Geoffrey Hinton, who not only was the senior author on AlexNet, but also on many, many other innovations in neural networks, he received the Nobel Prize for Physics in 2024. So let's look a little bit into this. So here you can see the architecture of the neural network. So to the left is the image, and you can see this has a certain width, so that's the RGB values, and other than that is basically the X and Y dimension of the image. And here you have the output, those are the 1,000 categories, and in between you have a layering, a so-called convolutional neural network. So it was not just the mere layers fully connected, as I've shown you in the conceptual figure a few slides earlier. So that is the reason. AlexNet is really the main reason why neural networks became so successful, and AlexNet was so important because it addressed the problem of how to deal with images on the internet, which was not really addressable before. However, there were three other aspects which really play a very, very important role in these developments. And one was standardization and open source. So Google hired these people immediately and built up infrastructure to compute neural networks. And they published this. So they could have kept this secret to the company and not release it to the outside. But I guess they were driven by the need for programmers that could use actually neural networks and program them. And that led Google in 2015 to publish TensorFlow. 2 years later, Facebook followed with publishing PyTorch. And TensorFlow and PyTorch are still today two of the main libraries that are being used to create neural networks, and in the labs you will use them as well. Another aspect that I think is quite important was the introduction of Google Colab in 2017. So Google Colab is a web-based development environment for code. And what is important about it is that you can collaboratively develop code, but another aspect is that you get easy access to compute. So you can choose whether you want to run on CPUs or on GPUs, and if you use the Google Cloud, then you can basically also use quite tremendous resources. So key aspect is that neural networks become large and they require a lot of compute, and hence if you want them to be taken up and people to easily develop stuff, you need easy access to large compute. And Google Colab is one way that smoothened the access to large compute in the Google environment. Interestingly, there are other competitors or collaborators. There is a very interesting company called Databricks, which was founded a couple of years ago. It received a staggering $1 billion as initial investment, and investors were Google, Microsoft, and Amazon, which is pretty strange. Now, what is Databricks doing? Databricks is developing a web-based environment in which you can mix Python, Java, C, and other programming languages together with SQL. You can do that in a team of multiple programmers. But what is more important, you can plug in large databases and large compute resources. And the reason why Amazon, Microsoft, and Google are co-funding this company is, of course, that they want Databricks infrastructure to be in alignment with their cloud infrastructure so that the users of Databricks can actually also buy into the clouds of Google, Amazon, and Microsoft. So easy access to compute is a very, very important aspect in neural network research. Now, compute has grown tremendously over the last 500 years. Over the last years, the last 2 decades. And here to the right, you see the growth in compute of the top 500. So every so often, twice per year, the top 500 supercomputers are evaluated, and they work on a standardized math problem, and what is measured is the number of floating point operations per second that they are able to execute. And if you go back to the year 2000, the time when Google was founded, we were at teraflops. So tera is 10 to the power of 12. So the best machine worldwide could do 10 to the 12 floating point operations per second. Now go back 10 years, 2010, so roughly the time when AlexNet came about, and we were already at petaflops. So that meant 10 to the 15 floating point operations per second. So 3 orders of magnitude better. 2020, we have reached already exaflops, so 10 to the power of 18. And you can see this line is slowly tailing off, but it's still increasing, and that means watch out will reach zeta and iota. I think that a rough constant in this crazy development is that the largest computer is typically round about $150 million. And that means that the largest supercomputer 20 years ago was $150 million. But when you look at the largest computer 20 years ago, it could do teraflops. And if you look what your NVIDIA GPU graphic card can do today, then it's in the order of 80 teraflops. So that means what you have in your desktop or in your laptop today was basically the largest computer 20 years ago. And 20 years ago, the cost of what you have today was 150 million. This is a development that is so incredibly huge that we do not see anything parallel in, let's say, car manufacturing or in any technology that mankind is developing. And that growth in compute was really a prerequisite for the emergence of successful neural networks. And you see today it's absolutely crazy. NVIDIA, who produces these graphic cards, its share price is rising. The big tech companies buy the graphic cards of NVIDIA like crazy. There are delays in creating them. And it really seems that NVIDIA is really the main force that is fueling the frenzy in neural networks. But besides the growth in compute, it was, of course, the growth in data. And just as one representative picture, I took this one from Wikipedia, and it shows the growth of Wikipedia in gigabyte of the pure text. And you see 2000, when all of these developments started, there was hardly anything. Now we're at nearly 25 gigabyte. And of course, this is only one example of incredible amounts of textual data, of image data that have been created over the last years. It's difficult to get this data for images, so I try to find something similar for Instagram, WhatsApp, or how many images has Google in its index, and the numbers you find online are billions and trillions, but they difficult to verify, and it's also difficult to see how they grew over time. But I think it's absolutely clear, you know, from the number of mobile phones, from smartphones that is around, and the number of pictures that people take and then put into their status and so on, that the amounts of data are absolutely staggering. And this had led to the growth of neural network models. And here to the left, you see a plot that shows over time, from 1950 to fairly recently, the AI models that were being worked on and published, and the number of parameters that they had. And you can see here, up to 2000, it's mostly in the 100,000 parameters. And so if you think back of the MNIST example I gave you, there it was already that 28 by 28 pixels and 10 fully connected layers make up already 6 million. So that was out of scope in that time. And then you see from 2000 onwards a little growth, and then from 2020 you see really the crazy growth phase that we're currently in. And if you now look into zoom in from 2018 to 2024 to now, then you see here ChatGPT with really trillions of parameters. So this is 1000 times 10 to the power of 9. So this is over 10 to the power of 12. Bloom, which is an effort that is public by Hugging Face, Llama from Facebook, Palm by Google, and you see that the amount of parameters that these neural networks use is just absolutely staggering. So, where are these neural networks used today? Because of course we see very prominent examples like ChatGPT, but there's more. So first of all, let's stick to ChatGPT. It has, of course, a history. So when you go back to the year 2011, there was IBM Watson, and that was at the time a really big splash. It didn't use neural networks, it just used standard AI techniques, I think stuff like decision trees on Wikipedia content and other. And IBM Watson participated in a game show, and it could beat the human competitors. Yeah, and that was 2011. And now, of course, 2023, ChatGPT went online, and it's absolutely amazing what kind of capabilities in terms of interacting and producing correct answers in proper English, well explained, ChatGPT can deliver. But there's more to this. If you go, for example, into the biomedical domain, then this is a paper that was published in Nature, so one of the highest profile scientific journals there is in 2023, so very recent. And this showed what is possible in biomedical question answering. And you have success rates of over 65% accuracy with a system coming from Google. And it works on many, many corpora benchmarks which have been developed over the decades in biomedical question answering. And you can see that from 2020 to 22, how with the growth of parameters, the systems actually become better at answering biomedical questions. This paper is not yet published. It's on bioRxiv. It's very recent, from 2024, and I think it's highly political. There, Google introduces an automated system for medical diagnosis, so going a step further than just answering questions, but doing the proper diagnosis. And they show in this paper this figure over here that shows the top N answers, so from just the top 1 to the top 10 answers are being considered, and then what the accuracy is. And what they compare is the performance of their AMI system against clinicians and clinicians unassisted, just by standard search and by AMI. And as you can see, this is highly political, because the funny thing is that AMI on its own, without the clinician, performs best. The worst is the clinician on their own. And then the clinician with standard search is better, and the clinician with AMI is even better. This paper is not yet published. It's just in an archive online. That means it has not yet been reviewed. And there are, of course, a few odd things. That, for example, if the top 1 answer is considered that the clinician has an accuracy of less than 20%, that's a little bit strange. But anyway, I think this is document that a lot is going on, and the kind of thing that you experience yourself with using ChatGPT, that there are tons and tons of other projects and more specialized areas where you will really see tremendous change over the coming years. A traditional area where AI was being used is game playing, and the big news in 1996 was IBM Deep Blue beating the then world champion in chess, Kasparov. And at that time, Deep Blue was not using any neural networks. It just had automated the computation of a game-playing tree. And this was taken up 20 years later by Google with AlphaGo. Because chess is difficult, but by now I guess we all think, okay, it can be done. But Go has an even larger search space than chess has, and so that meant Go was much more difficult to tackle. And at the time in '96, it was not possible to tackle Go. It was only possible to do chess. 20 years on, with the help of neural networks, AlphaGo was released, developed by DeepMind, the daughter company of Google. Self-driving cars are reality today. So in the 1950s, you had pictures like this that envisioned how self-driving cars would one day be possible. In 2007, you had already very realistic experiments going on. Like here, this is a DARPA competition where self-driving cars were going through the desert. So that means no pedestrians, but also no help such as lines on the surface and signs. And as of fairly recently, self-driving cars are reality. So this is a screenshot of a Waymo taxi that is driving around in San Francisco. And that is there, I think, from 2023 onwards. So self-driving cars are a reality, and neural networks that do the image processing and the evaluation of the sensors are a key driving factor for self-driving cars. And image analysis is not, of course, only used for self-driving cars and for image classification, but also in medical diagnosis, where we have a lot of image material. So this paper was published in Nature Medicine in 2020, so again, very high profile. And it's again a system by Google where they applied neural networks to do diagnosis of skin diseases. So you see this here to the left. You have some rashes on the skin, some red spots, and Google performed their automated system DLS in blue against a dermatologist in green. And red and beige are less qualified medical personnel. And as you can see, the automated system outperforms the dermatologist and has actually the best result here for the top 1 prediction and here for the top 3 prediction. Now, what is absolutely amazing is that Google has integrated this system into Google Lens. So if you actually point your Google Lens at a skin rash, it will give you a diagnosis. And what is scary also about that, that the original system was computed from 60,000 images, if I remember correctly. But of course, with Google integrating such a system into Google Lens, they will very quickly scale up their database of images. And now you could argue, well, but that's just the images, not the diagnosis. Well, but then they hire just a couple of doctors who do the diagnosis based on the images, and then they've got the full training data. So when that system that was published in 2020 was on 60,000, it's absolutely clear that by now Google has probably the best data set and is able to do much, much better with a growing data set. Now, another application where neural networks were quite successful is structure prediction. And that is very dear to my heart because it's a very old problem, a 50-year-old problem in biology. And bioinformaticians from around the world have worked on this for many, many years. For the last 2 decades, there was a competition where teams from all over the world tried to solve this problem. And the problem is how to predict the 3-dimensional structure of a protein given its sequence. So protein are the main building blocks of your body. So every cell is consisting out of many, many proteins. So it's basically the living material. And a protein is produced as a chain of 20 amino acids. And these chains can have 300 characters, 1,000 characters, 2,000. There are some exceptions of very, very long proteins that build up your muscles with 60,000. But generally, the average in human is around 300 or so. So these 300 characters, they form a chain, and they, in the cell, then adopt a 3-dimensional structure. And they do so always in the same way. And Google made a big splash in 2021 when they published this Nature article after winning the CASP competition, because through a neural network, they had solved this problem. And in fact, this is considered such a huge advance in the sciences that the Nobel Prize of Chemistry in 2024 was awarded to the DeepMind team. That's the AI daughter company of Google that is based in London, for this great achievement of AlphaFold. Complementary to AlphaFold is the design of proteins. And here's a paper published by Madani et al. In Nature last year. And this is co-authored by Richard Zocher, who is actually originally from Dresden and who's living in San Francisco. And he's the co-founder of a novel search engine called U.com, which is using large language models for improved web search. So on the side, he has also done work on using neural networks to create amino acid sequences given text. So he has not turned an amino acid sequence to a 3D structure, but rather text into an amino acid sequence. And they can prove that the desired function, which was expressed in text, is actually implemented by the amino acid sequence that they created. And that amino acid sequence was not an existing one, but a new one that was not available in nature. Another really big impact in the life sciences was created by protein embeddings. And behind neural networks and behind ChatGPT and many of these successes are so-called large language models. And the idea is here that you take input such as a sentence, for example, you cross out one word and you train a neural network to repredict that word. And what this neural network creates is an implicit representation of language. And instead of doing it on sentences, you can also do that on amino acid sequences. And this has been done in the life sciences. So all of the amino acid sequences that were available, billions, have been used, and characters have been blanked out and repredicted. And this creates a statistical representation of an individual amino acid sequence in the context of the billions of amino acid sequences that exist out there. And turns out that this statistical representation, called protein embedding, is much, much, much better than the original amino acid sequence. So for many, many training tasks, these embeddings are able to solve prediction tasks much, much better. So they have been very quickly adopted and are used all over the place instead of amino acid sequences. So with all of these successes, which are really staggering, is it the case that essentially all of artificial intelligence equates to neural networks? And that's of course not the case. Artificial intelligence is a very, very big field and is very multidisciplinary. It ranges from philosophy with reasoning, learning and perception, through mathematics with logic and proof theory, economics with understanding what rational decisions are and game theory, linguistics with an understanding of language, neurology with brain functions. And it has also, AI has such a long tradition. The developments are not all recent from the last century or so, but you can really trace back the very beginnings of AI to the 13th century, and well, maybe the true beginning of AI I would call the 17th century. And I would just want to give you those two hints because I found them really remarkable. So in the 17th century, long time before any electronics was there, and before the math was developed, before programming, etc. was there, there was already a very, very smart idea by a philosopher called Ramon Lull, and he created what is called the Ars Magna. And the Ars Magna was essentially this circular shape that consisted out of 3 rings, and each ring had 9 letters, and they corresponded to categories. And essentially, it allowed him to build all the 9 times 9 times 9 combinations of these categories. And the categories were things like goodness, greatness, eternity, power, wisdom, will, virtue, truth, glory. And the relations that they could engage in were difference, concordance, contrariety, beginning, middle, end, majority, equality, minority. And then he built basically combinations like this one over here, which corresponded to the question if goodness is great in relation to concordance. Now that sounds a bit strange, of course, but the key point was that he exploited combinatorics to ensure that he has a complete think through of all of the possibilities. So he would sit down and create really all of the possibilities and then think himself through whether the answer is yes or is no. And obviously he had not yet automated much of it, but he had systemized that. And I think that's a very, very important step to view reasoning as something that can be captured in a systematic way. Then big jump forward to the 17th century, and that is really the start of AI. And it's something pretty amazing, I find, still today, because computers were not invented, and Leibniz, who is the main character here, actually even created a computer which he couldn't implement himself properly, but it was then recreated for him, and you can see it in Munich in the Science Museum, and it's actually working. And Leibniz's idea was that he wanted to link math and philosophy, and that was until then never ever possible. When Ramon of Lull did his work, he was purely a philosopher. He was not a mathematician. Now Leibniz is trying to link reasoning to computation. And the way that he does that is actually really smart, because he's saying that the concepts that he wants to reason about, he represents as numbers. And basic concepts become prime numbers, and complex concepts become the multiplication of these prime numbers. Let's take a look at a quick example that he introduces at the time. He says, for example, let's assume that an animal is a basic concept with a prime number 2, being rational is a basic concept with a prime number 3, then a human, which can be defined as a rational animal, would correspond to 2 times 3 equals 6. And he further assumes, now let's just consider that monkey would be 10, then we can automatically infer that monkey and human are not the same, as 10 divided by 6 and 6 by 10 have a rest. That monkey and human have the concept animal, namely the 2, in common, but that monkey does not contain the concept rational. And then Leibniz goes on after illustrating this example. He says, I assume that somebody else will sit down and produce these characteristic numbers. And that's, of course, a very, very difficult task. Why is being rational a basic concept? And why is it 3? How many basic concepts would there be? So I sometimes wonder whether Leibniz said this as a joke or whether he really believed that somebody would sit down. But anyway, he was the first one who linked computation and reasoning, and for that he really deserves the credit as being the one who for the first time implemented a working AI. For a long time after Leibniz nothing happens, and then things picked up over 100 years ago with advances in math, in computing, in the advent of programming languages, and of course also basics such as neural networks that were introduced really over the 20th century. So historically, neural networks are not everything, but also practically in AI, neural networks are not everything. And so in this lecture, we will look also a little bit beyond neural networks, and one specific application or one specific other area we'll look into is probabilistic reasoning with a Bayes theorem. We will work specifically on a problem of classifying SMS as spam or as ham. We have a specific data set of several thousand SMS messages, and they are stuff like, congratulations, you're awarded 500 of CD vouchers or 128 gift guaranteed, where I guess you would immediately say that looks like spam. And we will employ the Bayes theorem, which you should know from your math education, to reason over whether it's more likely, given the words that we encounter here, that it's spam or that it's ham. And our Bayes classifier, though very simple, it will actually work fairly accurately. Another area is learning with decision trees. And the problem here is we want to decide whether to wait or not to get a seat in a restaurant. And the difference here is it's not text messages that we have or images, but rather it's tabular data with attributes such as, is it the weekend? Are we hungry? What is the price of the restaurant? Is it raining? What type of food is it? And so on. So we have all of these discrete valued parameters organized in a table, and now we want to define rules that allow us to take the decision on whether to wait or not. And the approach we will take is to look at the information gain of all of the attributes using the concept of entropy, and then iteratively selecting the best attribute to home in on the correct answer. Then we will look at unsupervised learning, because a big caveat of neural networks is that you need tons and tons of training data, and that is difficult to get. Categorizing 15 million images into 20,000 categories is really a lot of work. So supervised learning has these big disadvantages, and actually Bayes and also decision trees, they're all supervised. So how can we do without that supervision, without the training data? And there are some approaches which merely evaluate the data, and therefore they don't need any labels. And that also means that they work for small data sets, that we do not really create problems and do overfitting if we haven't seen enough data. And techniques are k-means, hierarchical clustering, principal component analysis, and t-SNE, which, by the way, is also by Geoffrey Hinton, the Nobel Prize laureate of this year in physics, and multidimensional scaling. And these are very, very practical techniques that are used in data science all over the place. So pay good attention. It's likely that in your future life you come across them. And finally, we will conclude the course by looking deep into natural language processing, and we will look at entity recognition and relationship extraction in a bit more depth. So the structure of the course is that we have 4 units on neural networks from next week on, and we will, after that, look before Christmas at alternatives to neural networks, as I mentioned, and then after the break, we will look at natural language processing in a bit more detail. So take-home message, you should by now understand the basic concepts of neural networks, such as neurons, the layering, forward propagation, backward propagation, what the loss function is, what the activation function is, what an epoch is, the batch size, the step size, and what a fully connected layer is. You should be aware of different examples of neural networks and where they are apparently already today very, very successful, and you should understand what ImageNet is, AlexNet, MNIST, and Leibniz Lingua Universalis. With that, thank you very much, and we'll see you in the next lecture.